Hi everyone. So we talked about at the end of class today that we didn't have enough time to get to Le Chatelier's principle and to finish off the lecture slides that I wanted to. Some of you had lab this afternoon, and so hopefully your instructor went over it. Most of you, at least the majority, will have lab tomorrow. And so I'm going to let the instructors know that at least my section, and I don't believe, but don't quote me on this one, I don't believe Dr. Sears' section has also got this far in lecture. So what I want to do is to just do a really quick overview of the concepts that you'll be analyzing in lab. So this is not meant to be taken as a definitive lecture or a stand-in lecture for what we will discuss in our next class. What I want to do is essentially I'm going to read you through the slides, and as I get to certain points, I may clarify certain definitions or give you a more intuitive sense to fully understand what we're talking about right now, or rather what we will be talking about shortly. 100% come to lecture, pay attention in lab. It's pretty intuitive. It's the idea of, do you know how a seesaw works? Once you know how that works, we can apply that really easily to a reaction and figure out how can we shift or we're not really shifting equilibrium, but how can we shift the amounts of products that we have depending on how we perturb a system. So what I want to do, again, it's just going to be a quick rundown of the basic information that I think you'll need to know before going to lab tomorrow. So the first thing I want to start with is we've been talking about Kc, right? So the equilibrium constant in relation to concentrations. The new idea or new variable I want to introduce is something called the reaction quotient, or Q sub C. If you'll notice over here, it's the exact same setup as QC. The only KC. The only difference is that it's not at, or not necessarily at, equilibrium. So before, when we had Kc, it was the products raised to their exponents. So c to the c, d to the d, a to the, or then divided by reactants, which is a to the eighth, b to the bth. You'll notice this is sub t at each of these variables. It just means at some time, which means it may or may not be at equilibrium. So let's read through the definition. The reaction quotient, QC, is defined in the same way as the equilibrium constant, Kc, except that the concentrations in QC are not necessarily equilibrium values. So in this sense, you will be given concentrations of products and reactants, and you're saying, okay, under these conditions, will it proceed towards equilibrium by either converting reactants to products or vice versa, products to reactants? So what we'll notice is that if QC is less than Kc, so it's taking the raw data of here are our concentrations of products and reactants, and that ratio is less than Kc, it says the net reaction goes from left to right, or rather reactants to products. Think about this, write this down in terms of products over reactants, right, when we're talking about in terms of size of denominator or numerators versus denominators. So if QC is less than KC, the only way that's possible is if the denominator is larger than the numerator. Our denominator is always reactants. So the only way to approach Kc is to make that denominator smaller. So the reactants needs to decrease while the products subsequently increase. So that's why we move from reactants to products. If QC is bigger or larger than Kc, again we think about the ratio. That means the concentration of products, which is the numerator, has to be larger than the concentration of the reactants. If that's the case and it needs to approach Kc, which is our equilibrium concentrations, the only way to alleviate that high QC is to convert products back into reactants until that ratio equals Kc. In those circumstances where QC equals Kc, no net reaction occurs, and that makes sense because everything's in the correct proportion And we've mentioned before that if a system is in equilibrium, if it's not perturbed, it will constantly stay at that ratio of reactants and products. So this is a little bit more of a visual representation of QC versus KC, right? So in the first example on the far left, you'll see that QC is less than KC. Again, I recommend writing out the expression for QC and KC. You'll realize that the only way QC can be less than KC, again, is if the reactants are in greater excess than the products necessary for the correct ratio for the equilibrium constant. The only way that can happen is to convert more reactants to products until QC equals KC. And then you have on the far right the same example in which QC is greater than KC. Again, the only way that can happen is if the products are in greater excess than the reactants according to the equilibrium expression. The only way it can move towards equilibrium is if more products are converted back into reactants. So what we're seeing here is if we play with different sides of the reaction, if we add more reactants or we add more products, we can convert what direction the reaction is going to move in. And so this leads us to Le Chatelier's principle. So French name, I know a lot of people have come up to me and said, I don't even know how to pronounce this guy's names. So it's Le Chatelier. So he came up with, French guy, it summarizes as if a stress is applied to a reaction mixture at equilibrium. So a stress can be summed in a couple of different ways, and we'll define that in one moment. It says the net reaction occurs in the direction that relieves the stress. So what you want to think about is having either a balance or a seesaw. If you apply stress in one direction, how do you relieve that stress on the system? It wants to regain equilibrium. So ways in which we can perturb the equilibrium of a particular system is to change any of the concentration of the reactants or products. So you can add more by, if it's a gas, you pump more gas in, or can you remove gas out by applying a vacuum so you can change the concentrations. Same thing with adding more or less liquid reactants or aqueous reactants. You can change the pressure and the volume. Specifically, that's going to affect gaseous reactants and gaseous products. And the temperature of the reaction can be changed. So there's plenty of ways that we can perturb the system away from equilibrium, and we know it will always go toward equilibrium, or at least even establishing a new one if you change the temperature. So let's read through some ways in which changing the concentration can affect the overall equilibrium. So we'll read through it. In general, when an equilibrium is disturbed by the addition or removal of any reactant or product, so we're talking about changes in concentration, Le Chatelier's principle predicts that the concentration stress of an added reactant or product is relieved by the net reaction in the direction that consumes the added substance. This means if I add more to the reactant side will be consumed to produce more products. If I added more products, what's going to happen is it's going to shift the reaction back towards more reactants until it reaches the Kc. So the ratio between the products and reactants is at the equilibrium ratio. It also states the concentration stress of a removed reactant or a removed product is relieved by a net reaction in the direction that replenishes the removed substance. The idea is if you remove products, what's going to happen to alleviate that stress is that more reactants will react to try and make more product to fill in that gap. So if you removed product, you need to make more product. So what's going to happen is it shifts the equilibrium to the right or towards the product. If you remove reactants, what's going to happen is the system tries to respond, and what it will do is takes the product and then breaks the product back down into reactants to remove that stress of removing product. So again, think of the idea of a seesaw. If you take some weight off from one end, from the left side, some weight from the right side needs to move to the left side to go back to a balance or equilibrium. So this is just summarizing it. I don't recommend memorizing this, but if it helps for tomorrow's lab, go for it. I have much better visuals, I think, that I can draw on the board. during our next lecture, but let's just take what we got here. So it's saying any changes marked in blue shifts the equilibrium to the left. And this is what I was talking about, the idea of a seesaw. So if you decrease N2, right, over here, the only way, so that's like having the seesaw tilt like this, right? No, sorry, tilt like this. Sorry, it's decrease. So you have a lighter person on the left-hand side. So you have, this kind of goes up in the air. The only way to bring that back down is to take some weight from the right-hand side and bring it back down till it hits equilibrium. So if you decrease N2, so NH3 will break apart until reform the reactants to try and, or will eventually hit equilibrium. The same thing if you take off or take away some of the H2. Again, you've decreased, if you think of it in terms of a seesaw, the mass goes up. Well, I got to put more on the left-hand side, so I take it from the right-hand side until it comes back down to equilibrium. And then you see in the red, right, any changes marked in red shifts the equilibrium to the right. Well, if I'm thinking about a seesaw again, right, if I increase the how much N2 I have, it's like putting a heavier person on the seesaw, and it comes down, so you have a seesaw shifted like this, and the only way to make it equal is to shift some weight to the right-hand side until it hits equal again. And you can apply the same rationale to this side of the equation with a decrease in the increase. So let's take a look at this visually. So I've mentioned before that if we have a system that's allowed to reach equilibrium, and so we've used this equation before, or this chemical reaction before, which shows the Haber process of nitrogen reacting with hydrogen to form ammonia. I said if the pressure and the temperature has remained constant and it hits equilibrium, it will remain that way forever, which is true. So what we see here, we have these relative concentrations of H2, NH3, and N2. And so QC equals Kc because the concentrations are at the equilibrium concentrations. This next portion shows that if I really quickly open that container and then dump in a bunch of N2, so you see this spike in N2, what's going to happen? What ends up happening is we increased the reactants, so what the reaction is going to try to do to alleviate this stress on the left-hand side of the reaction is to push towards the right. So what we should predict is a decrease in N2, a decrease in H2, and an increase in ammonia. And it's exactly what we see here. So there's our decrease in N2 as it's consumed to push to the right-hand side of the reaction. There's our decrease in H2, which is 3 times faster than this. And this this harkens back to talking about chapter 14, when we're talking about relative rates. So this decreases 3 times faster because of a ratio of 3 to 1, but the H2 decreases, and the concentration of N3 increases because what it's doing to alleviate that stress of adding more N2, it's pushing towards the reactant, the product side, to establish a new equilibrium. Once this new equilibrium is established, so go prove to yourself that the QC in this particular instance is going to be less than Kc. We said if it's less than Kc, it's going to be moving towards, the products, and we establish a new equilibrium. One of the rules that we wrote down before when we were talking about equilibrium is that the rates are equal to each other. The forward and reverse reaction rates are equal, but the concentrations are not. And this is a really good example of that. Both the initial and this new final equilibrium are both in equilibrium, but you can obviously see that the concentrations are quite different. But this is only based on the amounts that are there. So the forward and reverse reaction are equal, but the concentrations aren't necessarily equal at all equilibrium. So let's think about changing in concentrations. I'm just going to really breeze through this. We'll obviously do this on the board next time because I think it's really important to break down how to approach mathematical problems. But let's take this real quick. We have the Haber process again at 700 K with a Kc of 0.291. We have these certain amounts, so we have N2, H2, NH3. It's disturbed by increasing the N2 concentration to 0.15 molar. We take a look. So we put in our concentrations for QC. Well, I didn't change any concentration in the ammonia, right? It remains still at 1.98 molar. I keep the same concentration of H2. So there's our NH3, there's our H2. Then we have our nitrogen, which we said we increased to a concentration of 1.5. Well, there's our 1.5. You plug that into QC, we find out we have an answer of 0.0968. That is less than the Kc that we have been, that's a literature value for Kc. So we read down here, since QC is less than Kc, more reactants will be consumed. So it means it's pushing toward from this side of the reaction to this side, and the net reaction will move from left to right. And so I think you've may have heard that I've been saying going from left to right or right to left. The way that it's written, it's just, I guess it's colloquialism. When chemists talk, when they say the left-hand side of the reaction, they mean the reactants, and the right-hand side of the reaction means the product. So it is 100% very common to run into people saying the left-hand side or the right-hand side of the reaction. It just means reactants and products. So the reason why we have this slide in here is this is one of the reactions that you'll be doing today if you've done it, or tomorrow in the lab, of looking at how you can actually visually inspect how a reaction pushes to one side or the other. So we have an indicator. We can go over this more in lab if you're interested in it. But methyl orange is a particular molecule that as the acidity goes up, so more H3O+, so more hydronium, it's going to turn red. As the hydronium goes down, it turns yellow. And so you actually can get a colorimetric or color meter, right? So color measurement. So colorimetric measurement of how this is shifting between equilibriums. As it shifts more to the left, it turns yellow. As it shifts more to the right, it turns red. Alright, so we talked about changing concentration, so now let's talk about changing pressure and volume. So in general, when equilibrium is disturbed by a change in volume, which results in a corresponding change in pressure, Le Chatelier's principle predicts. So this is talking about changing pressure so don't think about pressurizing something like you pressurize a tire, where you add more gas to it. Think about pressurizing it in the sense of a piston. So if you crush something inside a piston, because the volume is being decreased, the pressure goes up. So in this case, think piston, don't think about filling up a tire. So an increased pressure by reducing the volume, that makes sense, think of a piston. You decrease the volume of a piston, it increases the pressure below the piston as long as it's a closed system. This will bring about a net reaction in the direction that decreases the number of moles of gas. So you want to think about the idea of decreasing stress on the system. If there's less moles of gas, that means the pressure is going to not change as much. So if the pressure, if you have molecules flying around at equilibrium, and there's a certain amount of molecules, and it has the option to reduce that number of molecules. If the number of molecules is reduced, the pressure decreases. So what you're trying to do is you're pushing towards the side that has the least amount of molecules as the volume decreases. The volume decreases. And the opposite, if the pressure decreases by expanding the volume, so this is the idea of a piston being pulled up, this will bring about a net reaction in the direction that it increases the number of moles of gas. That's really abstract. Again, this is why I want to have a more in-depth lecture the next time we meet, but again, try and internalize this. I'm going to give a quick example on this. So we take, again, the Haber process, N2 plus H2 goes to ammonia at a certain temperature with a certain Kc. It says the equilibrium mixture, this time we have a half a molar, 3 molar, and close to 2 molar, is disturbed by reducing the volume by a factor of 2. We're going to see how this happens. So if reducing the volume by a factor of 2, and we've only assumed that we can change the volume because we're assuming it's a piston. So you have a box, it's at a certain equilibrium, and now we just crush that volume by half by basically taking the roof of that container and just pushing it down by half. So what that ends up doing is, if we look here, here's our concentration of NH3. Remember, concentration is moles per volume or moles per liter. So if you change that by a half, you're actually going to increase your concentration by 2. So you'll find out 1.98 times 2 is 3.96. And that's going to be squared because it's based on our equilibrium expression or our equilibrium coefficient expression. N2 was at 0.5. Well, it increased, the concentration increased by 2. There's our 1. There's a concentration originally of H2. It increased by 2 because their volume was decreased by half. So there's our partial pressures. We find out that the QC is less than KC. So again, what's going to end up happening is because the QC is less than KC, more reactants will be consumed, and the net reaction will go from left to right. So we could see this in two ways. One, just by plugging in the mathematical values of QC, that's very beneficial, especially if we have concentrations. It's easy to calculate. We can also see up here in this net reaction, and we've alluded to this before when we were talking about delta N, but if we're talking about trying to reduce the pressure, so if we crush the ceiling, so we've taken a box and we push the ceiling down by half, so we increase the pressure because the volume went down. One way we can alleviate that increase in pressure is just reduce the number of molecules we have in there. So at equilibrium, if we look on the left-hand side, we have 1, 2, 3, 4 molecules of gas if it's mostly reactants, or 2 molecules of gas if it's just ammonia. Well, if we apply stress on the system by changing the volume by half, so you increase the pressure by 2, well, one way to alleviate that increase in pressure is just to have less things smashing into the side of the container, right? Because our definition of pressure on the microscopic scale is the number of collisions of molecules with the side of the container. Well, if you have 4 things smashing against the side versus 2 things, well, this pressure is going to be a lot less if you have 2 things smashing against the side versus 4. So again, we can see it mathematically, pushing towards the reactants, and we can also see, how do we want to phrase it? I don't know. I can't want to say tangentially, but that's not correct. But have something tangible, right? We see that we have 4 things versus 2 things. Well, the pressure goes down when I have less things flying around, and so I want to alleviate that increase in pressure by having less molecules around. So again, we go from left to right. We take a look at this. Here's another one. This is getting into, it seems counterintuitive, and I remember having a hard time myself trying to internalize this. We'll go over this a little bit more in class. It seems it's cutting off the bottom of my slides, so hopefully that works out for you guys. So we've talked now about changing concentration. We've now talked about changing pressure, and now we're talking about changing temperature. Changing temperature, we need to know the enthalpy of a reaction. So, again, we take the Haber process. It is an exothermic reaction. It releases per mole of reaction negative 2,043 kilojoules. So we know it's exothermic. This might be a little bit more hard to internalize, but let's read the bottom. As the temperature increases, the equilibrium shifts from the products to the reactants for this particular reaction. We're shifting from here to here. Most of us think that as we heat up reactions, it is true the rates of reaction increase, but the equilibrium, because remember it's a ratio between the forward and the reverse, and both of them are affected by temperature. If it's exothermic, it actually moves back towards the products. So if we heated this reaction up higher and higher and higher, it's going to form a new equilibrium mixture in which the reactants are favored. One way we can think about this is because it is exothermic, we could rewrite this as N2 plus 3H2 equilibrium with 2 ammonia plus some energy. And if we treat energy like it is a quantity or a reactant, it's not a physically real way to think about this, but abstractly it actually helps us understand what direction we're going to go in. If this counts as part of the seesaw analogy, right? That means if we add more energy in the form of heat, that means technically we're kind of tilted this way. So the only way to approach equilibrium is if we start moving more mass to this side. So eventually we'll go back to equilibrium, and the only way to do that was to create more reactants. So as you heat exothermic reactions, they actually produce less products. Seems counterintuitive, but it's only counterintuitive because we assume, which is true, that reactions go faster when they're heated, but we've got to remember that equilibrium big K is a ratio between forward and reverse reaction, which are both affected by temperature. So here's a summary. In general, when an equilibrium is disturbed by a change in temperature, Le Chatelier's principle predicts that, and so slowly let's go through it. The equilibrium constant, so that's Kc, for an exothermic reaction, a negative delta H, decreases as the temperature increases. The equilibrium constant for the endothermic reaction, positive delta H, increases as the temperature increases. So let's make sure that makes sense. Well, actually, I feel like this is where it becomes more difficult to explain via an online lecture. So this goes back to what I was just saying about how K, right, is a ratio between the forward and reverse reactions, and both forward and reverse reactions are affected by temperature. You actually get a new K for the change in temperature. So we will address this much more in depth when we have a lecture on either Friday or Monday, whichever class you're part of. But just realize that as the temperature changes, so I feel like we're doing a bad job on this right now. There's two ways to think about this. One is looking at how temperature affects it in terms of if we just treat temperature as a reactant, which was the first example that I gave. The other one, and which I also said was a poor example, but helps you decide what direction the reaction is going to go in if you perturb it with heat. The actual real physical process that's happening is that when you change the temperature, you're actually changing K and not changing Q. So that's something we're going to go into a lot more in depth on either Friday if you're my Monday, Wednesday, Friday class, or Monday, Wednesday if you're my Monday if you're my Monday, Wednesday class. So again, that's what I just read off. We can take a look. The last slide that we have right now is going to be talking about the effects of catalysts on equilibrium. So this is a little bit of a simplified version of when we're talking about catalysts, right? We'd already defined catalysts. We said they don't actually reduce the activation energy. They just take the reactants on a different catalytic pathway or a different mechanism to reach the products. We originally said that it's like a difference between summiting a mountain versus finding a path that kind of goes around the summit. So you end in the same spot, you kind of took the same path, but it's a little less energy because you took that different path. If we make the assumption, and this is a pretty big just generalization, that the catalyzed pathway just in general has a lower activation energy than the uncatalyzed pathway, right? What we see is that the forward reaction and the reverse reaction, and for the catalyzed reaction versus the uncatalyzed reaction and the forward and reverse reaction of the catalyzed reaction, the ratio remains exactly the same. So a little bit funny to look at this graph, but the take-home message is catalysts do not affect the equilibrium constant at a constant temperature. So when you add a catalyst, you will make the reaction faster, but you will not affect the equilibrium concentrations. So it will reach equilibrium faster, but it will not change that equilibrium constant. And again, this is just what I wanted to talk about, just like let's get the general ideas there. We'll talk way more in depth on this when we meet next time. So again, hopefully we have class tomorrow, but if we don't, enjoy the snow day, but I will see you all very soon.